Differential equations, we're in section 4.6, day 2, working on what we did last time, the variation of parameters, but this time higher order. That is higher derivatives. We might see third derivatives, fourth derivatives, whatever it might be. Also, we'll take a look at a IVP, an initial value problem, for our second example. But take a look at this example right here to start us off. Y triple prime plus y prime equals secant. First, whenever you're solving one of these, again, assume that you're solving the homogeneous. The right-hand side was equal to 0 first. We always are working that out. And you don't have to take successive derivatives and plug them in. We've done this quite a bit. You will see rather quickly that you'd get m cubed plus m equals 0. You can factor that out, m times m squared plus 1, and with a zero factor theorem, or zero product property, you could call it that too, you will see very quickly that you will in fact have three different solutions. Two of them are complex right here, the 0 plus or minus I. You also have that 0. What are we getting at? You'll have your homogeneous solution would be e to the, well, with the 0, that's 0x, and forgive me, I should put a constant out in front there. We could call that c1. And then remember, when we have alpha plus or minus beta I, we're always going to have e to the alpha x, and then we'd have cosine of beta x plus another constant sine of beta x. And hopefully you can see very quickly that because alpha is equal to 0, this is going to work out pretty nicely. You can have 0x, that's e to the 0, that just becomes a 1. So you're going to be able to, again, answer very fast. You can see that you'll have your final answer right here is a C1 times 1. Now, I'm being very emphatic about that. You'll see why in just a second. You'll have C2 cosine of x plus C3 sine of 1x, because our beta is equal to a 1, right? So here's what I'm getting at. Right now, we can look at that and say, hey, we're doing so well. We've done a lot of this in the past. The problem is your right-hand side, that function is not in the table that we've had. And, we're not able to use the methods that we've been doing previously, writing general forms of the right-hand side and taking derivatives and finding those coefficients. But instead, what we're going to do is say, look, we're assuming that our particular solution is going to be some function of x times our y1, our first solution. And guys, that's why I wrote a 1 right in here. We had 3 distinct solutions. That's with that m to the third right there, when we were solving that. So we've got some function of x times 1, some function of x, we could call that u2 times the cosine of x, some function of x u3 times the sine of x. And at this point, the way we go ahead and find u1, u2, and u3 is working out the Wronskian and making another adjustment too. We're going to review that in just a minute. The last time we did a 2x2 system, or a 2x2 determinant. For our Wronskian, what you're going to do is always take your y1, y2, y3. So we'll have a 1, cosine of x, and then we've got sine of x. This is a 3x3 determinant. We're going to take derivatives. Derivative of 1 is 0. Derivative of 0 is 0. Derivative of cosine is negative sine of x. The derivative of negative sine of x is going to be negative cosine of x. Derivative of sine is cosine, and the derivative of cosine is negative sine. Now, to get our 3 by 3 determinant, you may definitely use your TI-89. However, and this is the honest to goodness truth, it takes a long time to get that typed in. It takes a lot of effort to get it typed in. So really what we'd like to do instead is just work this out honestly by hand. It's going to go more quickly. And to evaluate a 3 by 3 determinant, copy your first column that goes vertically. We'll say 1, 0, 0. And then copy your second column. That's your cosine of x, negative sine of x, negative cosine of x. Some teachers call this the basket weaving method. You can see why in just a second. Up on top we'll have plus, plus, plus. And what you do is you take these diagonals and you multiply them together. Look, 1 times negative sine is positive sine squared of x. The fact that you've got a plus here means keep it positive and then say plus. But look, your next diagonal multiplies to 0. That's just a 0. This diagonal here would multiply to a 0 also. So you could say plus 0 plus 0. It's kind of silly to do that. But then to finish, you're going to go like so. From the bottom, I'm going to write minuses. And we're going to multiply those diagonals and just change the sign to a minus and add all of those up. So let's see what would happen. 0 times negative sine times sine, that's 0. Negative cosine times cosine is going to be a negative cosine squared. But don't forget you also have this minus right here. And a minus times a minus we know is going to be a plus. And then negative sine times 0 times cosine and put a negative in front of it, that's going to wipe out. Well, it won't take you too long to see the minus and the negative turn to a plus, and sine squared plus cosine squared equals 1. And guys, that's your Wronskian, that's W. This is really known as the basket weaving method, and you can see why. When you have all your diagonals, they cross and they form kind of like a basket pattern. But we're not done. We found W, and that's well and good. Now we'd like to find W sub 1. And to find W sub 1, it's going to look so very, very much like our Wronskian that we had, with one tremendous difference. Your first column will be different. And your first column won't be a 1, 0, 0. Rather, it's going to be a 0, 0, and then our f of x. That's what will get changed for a W sub 1, also for a W sub 2, W sub 3. It's always going to be 0, 0, and then f of x on the bottom. The rest of the Wronskian gets copied, just as it was. So it's looking amazingly close, except for that first column. And then you have a choice if you'd like to type this into the 89. Again, that's actually going to take more time to work out. Copy your first column. It's no longer 1, 0, 0. Now it's 0, 0 secant. Then copy your second column, which is a cosine of x, negative sine of x, negative cosine of x. And you know what? You just do that basket weaving method again. And you can see it's only going to take a little bit of time. And the more you work out these 3 by 3 determinants, honestly, you're going to find that it goes very fast. Especially when you have zeros here. Look at this. The 0, negative sine, and negative sine. That wipes out to a 0. Here you get cosine times secant. Now, cosine times secant. Guys, cosine times secant is a 1. You know, those are reciprocal functions. Secant's 1 over cosine. So you're just going to have a cosine of x, or a plus cosine of x. Look at your next column right here. That wipes out to a 0. Then what? Well, then you're going to go ahead and multiply these other diagonals. Now, and remember, the negative on the bottom is very much in play. We'll have secant times negative sine times another negative. A negative and a negative turn into a positive. And you'll have sine squared. There are two of those. Then you'll also have that secant right there. Look, this next diagonal multiplies to a 0. It's gone. And the last one works out. So that's your W sub 1, isn't it? Now, we could go ahead and find W sub 2 and W sub 3. It wouldn't be difficult to do. But listen, I do want to immediately jump off to the side and talk about why we've been doing this. U sub 1 prime is W sub 1 over W. So U sub 1 prime, we just found this to be cosine of x plus sine squared secant x. And thankfully, my goodness, W you already found to be a 1, didn't you? So, hey, this is working out nicely. Let's just do a little bit of work off to the side. Up here, you'd have sine squared of x times 1 over cosine. And you could more or less say, well, that's sine squared over cosine. This thing, cosine of x, well, my goodness, we could get a common denominator, couldn't we? We'd multiply the top and the bottom by cosine. So we'd have cosine squared of x plus sine squared of x all over cosine of x. And that's 1 over cosine. And guys, that means U sub 1 prime is really secant. And we could go ahead and take a real quick antiderivative. We just did this recently. I hope you remember. It's going to be the natural log of secant plus tangent in absolute value. We'll ignore that little constant. Well, let's keep going here. We could say, well, what about W sub 2? W sub 2 goes back to the Wronskian, the original Wronskian. You had 1, 0, 0. But now your second column will be 0, 0, and at the bottom it's your f of x. Your third column was sine, cosine, negative sine. And tell you what, now we just have to work that out. I'm going to recopy the first column, recopy the second column. And like I said, you start doing this after a while, you're going to see that this picks up. Look at this. Your first diagonals are all going to be zeros. There's a 0 every single location. Look, when you go this way, this first diagonal right here is going to wipe out. Look, secant times cosine. Secant times cosine is a 1. Don't forget, you've got this negative 1 right there. And this last one just wipes out. Hey, look at that. W sub 2 is just negative 1. So, what are we going to do now? We're going to say U sub 2 prime is W sub 2 over W, just W, right? That's what we've got there. Much the same way that U1 prime was W sub 1 over W. So this is negative 1 over 1. It's just a negative 1. And tell you what, we're going to just integrate that. And this is way easier of a problem. You will quickly get that U2 is equal to negative x. We just have one more W sub 3 to take a look at. And our W sub 3, it's going to be your first column's the same in your Wronskian. The second column was cosine, negative sine, negative cosine. And then your final one will be 0, 0, and then f of x. And then we just recopy our first column, recopy our second column. This can get rather long, but we're going to pick this back up on our next video as we work this out, and then we'll be able to find U sub 3.